I'm going to do some Euclidean geometry with you guys. All right. So the first question we're going to have a look at is this one over here. Just a reminder, when you are doing Euclidean geometry, it is so important for you to read the information that comes with the diagram first. Sometimes they put all the information onto the diagram and sometimes they don't. So if you don't read the information, you're not going to know what's going on. I myself have made that mistake many, many times where, somebody will quickly come and ask me something, how do I do this? And I don't read the information and I look at the diagram and I look at the question and I can't work it out. And if I just read the information, I would have been able to do it. So please always start by reading the information that comes with every diagram, irrespective of whether it's geometry or not, but geometry, 3D trig, etc., etc. Okay, so in this particular case, we've got PQRS, which is a cyclic quad. They've told us that, although they didn't really need to, but we're glad that they did. When we see the words cyclic quad, there are two theorems that spring to mind immediately when we've been given a quad is cyclic. What are they? What are the two theorems that spring to mind immediately when we read the words cyclic quad? What do you think, Matrix? What are the two theorems we think of straight away? That's it, Teddy. So the exterior angle of the cyclic quad is equal to the opposite interior angle. Yes, indeed. In the case where one side of the cyclic quad has been extended. What's the other one? That's it. The opposite angles are supplementary or they add up to 180 degrees. Good. Okay. Next thing, PS is produced to W. That doesn't relate to a theorem. TR and TS are tangents to the circle at R and S respectively. So if we go, why are we, oh, sorry, there's R over there. Sorry, it was just a little bit hidden. So they've given us two tangents. So when we see the word tangents, what do we start thinking about then? Which theorems do we think about when we see the words tangents? So tan chord theorem would be one of them. Cool. Thank you, Gugu. What else? What else do you think about when you see the word tangent? Okay, Kalipa. So for there to be perpendicular lines, that would be radius or diameter perpendicular to tangent. All right, so then we need to have the circle center and we need to have a radius. I'm glad you're thinking about that. That's a very important reason. It's not going to be applicable in this case, but that doesn't matter. Tangent perpendicular to chord. So it's blessing, it's tangent perpendicular to radius or diameter. Okay, tangents from the same point are equal. Beautiful, Sagwadi, lovely. Gugu, tangents from the same point equal angles. You're on the right track. We've just got to be careful about how we set that out. Okay, so yes, when we see the word tangent, we think about three things. First of all, we think about tan chord theorem. If there's a circle center and a radius, we can use radius perpendicular to tangent. And the third thing that we think about, especially in a case like this where there are two tangents, is tangents from the same point. Okay, tangents from the same point are equal. And if we've got equal lines in a triangle, if two sides are equal, then we've got equal angles as well, because they would be angles opposite equal sides. Okay, the other thing that they tell us is that T is equal to 78. That's on the diagram. And Q is equal to 93. Now we are ready to start looking at the question. So the first one in 9.1 says, give a reason why ST equals TR. Well, I think someone's already said that. Why is ST equal to TR? What's the reason that they are looking for there? That's it, Nhlanhla. Well done. Okay, they are tangents from the same point. Cool. All right, lovely. So this is just out of 1 mark. So there would be 1 reason mark allocated there. Brilliant. Okay, now on to 9.2.1. Calculate giving reasons the size of, and these are both out of 2, so they shouldn't be too difficult to work out. First of all, they want the size of S2. So S2 is down here. Can anybody tell me what they think we need to do in order to work out S2 and to make sure that we get both of those marks? What must we do now? What's our starting point with calculating the size of S2? Okay, so the way that you're doing it is the correct way, but I want you to make sure that's it. So not 180 minus 78, yes, and then we've got to do something. The triangle equals 90. Rosario, I'm not sure what you're referring to there. Exterior angle of a cyclic quad, says Leanne. Okay, so Leanne, before we continue, all right, here is the cyclic quad. I'm just busy highlighting it in yellow. Okay, so the exterior angle of the cyclic quad includes angle S2, but it's not just S2. So what's happened here, Leanne, is that side PS, I'm just highlighting it rather badly, has been extended to W. So this entire angle here, S2 plus S3, is the exterior angle of the cyclic quad. Okay, so it's not just S2. S2 is part of that, but it's not just the entire thing. The thing is that if we use exterior angle of cyclic quad here, S2 plus S3 equals 93. So how then do we work out what just S2 is? So unfortunately, to get S2, we're not going to use the exterior angle of the cyclic quad to answer this particular question. Okay, so Gwadi, go for it. Do you have a question?
Hi, ma'am.
Hi, Sagwadi.
I think I have a way to solve 9.2.1.
Sure, go for
So,
it. Tell us what you do.
so in 9.1, we proved that ST and TR are equal. So we can say that S2 and R2 are equal because it's an isosceles triangle.
Mm-hmm.
And then since we have R2 and angle T, and we're looking for S2, we can use sum of angles in a triangle.
Beautiful. Beautiful. That's great. That's 100% perfect. All we've got to do now is put all of that down on paper. Fantastic. And some of you were saying this. I was just answering Leanne's question. So, Gwadi, there was a wonderful explanation. Thank you so much. Now, you're quite right. We need to explain why S2 equals R2. And it comes from what we did in 9.1, like Gwadi said. All right. So, if we hadn't have stated that ST equals TR and that they were tangents from the same point, we could be penalized for this. You have to state why the lines are equal to each other. So they could be given, or it could be tangents from the same point. But there needs to be an explanation. So what we could do here is say ST equals TR, and I could write the reason out again, or if I want to, I can say proved in 9.1. Right, or I could write the reason out as well. The deduction from that, as Sagwadi was saying, is that R2 equals S2. Now there needs to be a reason. This is angles opposite equal sides. So they don't like us to use the word isosceles triangle to explain this, even though what Sagwadi said was true. It is an isosceles triangle. All right, so we use the words angles opposite equal sides, which is something I'm sure you're all familiar with. Now we can do what you were suggesting, which is to take 78 away from 180 and then divide our answer by 2. So another way of setting this out is to say, well, if R2 equals S, then I can have 2 of S2. If I add 78 to that, I'm going to get 180 because of the sum of the interior angles of a triangle. So 2 of S2 is going to be equal to the difference between 180 and 78, which leaves me with 102. And now I can divide both sides by 2, and that means that S2 is equal to 51 degrees. Okay, so each step of the way I have substantiated what I've done. I've used the correct reasons. I'm definitely going to get 2 out of 2 for that. Okay, so 1 mark definitely on the answer. I'm not sure where they'd put the other mark in this case, but my guess is going to be on that statement reason over there, that R2 equals S2. That I think would be the most important thing to state. Okay, cool. All right, let's worry about 9.2.2. So now, Leanne, what you were saying earlier about the exterior angle of the cyclic quad, now we're going to use the exterior angle of the cyclic quad. I hope that makes sense to you. In 9.2.2, what are we going to do? What should I write? Maybe one of you can tell me. Now that I know what S2 is, how can I work out S3? S3 equals Q minus S2. Yes, it does, Nhlanhla. Okay, Mamelo. Angle in a semicircle is when you've got a diameter. So that's not going to apply in this case. When you've got a line that goes through the center of the circle and touches both sides of the circumference, it's a diameter, then it subtends a right angle at the circle. That's angle in a semicircle. Okay, that's not what we're doing over here. All right, do you remember in the beginning I gave Leanne that explanation why Q was equal to S2 plus S3? Do you remember that? That's it, Leanne. Okay, so S2 plus S3 equals 93 exterior angle of cyclic quad. And if S2 is 51, then as Nhlanhla said, I think it was Nhlanhla, S3 would be the difference between Q and S2. All right, so now we've got 93 minus 51. Whoopsie. 93 minus 51 leaves us with 42, as you guys are saying. There we go. That's at 42. I'm getting 42. That's it. Good, Gugu. Good, Amahle. Well done. Okay, so therefore S3 is equal to 42. Okay, so here I think they would give you a statement reason mark and then an answer mark over there. Okay, cool. Nice, easy question. Ease us into the swing of things. Are there any questions before I move on? Cool. Okay, let's go on to the next one. All right, so there's quite a bit more going on in this particular diagram than in the previous one. Okay, why can't we use tan chord? Okay. In order to use tan chord theorem, Teddy, there needs to be a triangle on the inside of the circle, not a quadrilateral. So tan chord theorem, when you want to use tan chord theorem, I'll tell you what I'll do. I'll just scooch over. Teddy, this is not going to be the best diagram in the world, but this is when you use tan chord theorem. So you've got a circle and you've got a triangle, whoopsie, on the inside of that circle and a tangent at one of the vertices. Tan chord theorem tells us that the angle between the tangent and the chord, so that's going to be this angle over here. Here is the tangent, here is the chord. Subtends the angle in the alternate segment, so it's going to be that one over there. So can you see it's a triangle inside the circle, not a cyclic quad? Okay, Teddy, that's why tan chord theorem in this case is not applicable. Does that make sense?
Thank you, ma'am.
No problem. Pleasure. Okay. Cool. And yeah, please don't be afraid to ask. There are no silly questions. This is your opportunity to clear up your misunderstandings and things that are confusing and whatever the case is, so that you can do the best you possibly can in those upcoming final exams. Okay. All right. So let's have a look at question 10. Again, we begin by reading the information. So in the diagram, they tell us BE and CD are diameters. Okay, so now who was it that said angle in a semicircle? I can't remember. Just going to go back quickly. There we go, Mamelo. I'm glad you brought that up. All right, because we're going to use it now. All right, we've got a diameter and the diameter, well, we've got two diameters actually, and the diameters will subtend right angles at the circle. So if we look at diameter CMD, which angle is equal to 90? If we look at diameter CMD, which angle is equal to 90? Well done, Amahle. Okay, so now Mamelo, look at Amatle's answer. She said A1 plus A2. That's very important. When you say A, Mamelo, you mean the whole of A from 1 through to 3. Okay, so you cannot call A1 plus A2 just A. All right, so be very careful. You're not the only person who does that. Lots of people do that. So you can either do what Amahle said and call it A1 plus A2, or you can say CAD or DAC. You can refer to it like that as well. That would be acceptable. All right, so just be careful about how you name angles. If it's been cut into more than one piece and you only want part of it, you can't just call it the letter. Cool. Okay, so that's one 90-degree corner that we've got. What's the other 90-degree corner that we've got? Now, this is a little bit confusing. BME is also a diameter. So what else adds up to 90? BME is also a diameter. So what else adds up to 90, Matrix? EAB, good. Or A2 plus A3, beautiful, good. Well done, everybody. All right. So that over there is also a 90-degree corner. Okay, then they tell us M is the center, all right, so that means we've got radii as well. Not sure we're going to use that. Chord AE is drawn to cut CD at F. That doesn't relate to a theorem. Then they tell us that AE is perpendicular to CD. AE is perpendicular to CD. So that explains why this angle over here at F is equal to 90. Now that is important. All right, so now I'm dropping some hints here. Okay, you have got a line from the center and it is perpendicular to a chord. What does that do? What does the line from the center perpendicular to the chord do? It bisects the chord, absolutely. So it cuts the chord in half. So by them telling us that AE is perpendicular to CD, what does that really mean? It really means that AF equals FE. Okay. So the line from the center perpendicular to the chord bisects the chord. Now, a lot of people get confused between line from center perpendicular to chord and line from center to midpoint of chord. So the words you use depend on what you've been given. If you are given the 90-degree corner, you say line from center perpendicular to chord. Okay, it bisects the chord. If you've been given that F was the midpoint, then you would say you would be proving that F was 90, then you would say line from center to midpoint of chord. And they don't like the word bisect, it's got to be to midpoint of chord. Yes, line from center perpendicular to chord is the correct reason in this case. All right, and look, there we go. All right, do you see how if we read the information and we start processing it and linking it to our theorems, we actually end up answering some of the questions. So now again, give a reason why AF equals FE. And Yamkela, you've put it beautifully there for us. It's line from center perpendicular to chord. Okay, and we would get obviously our reason mark for stating that. Okay, now on to 10.2. Oh, by the way, C is equal to X. That was the last bit of information that they gave us. All right, now in question 10.2, they want us to determine the size of M1 in terms of X. Okay, so we go to the diagram and we identify M1 over here. Now, what we want to try and do is see how M1 is related to the information that we already have. Is M1 inside a triangle? Is it the exterior angle of a triangle? Is it an angle at the center? We've got to try and link these things to all the stuff. One of the corollaries would be equal chords subtend equal angles. You could start thinking about that, Leanne. But at a glance, we can see that angle M1, does that help us? Angle M1 is the angle at the center. But do we have, yes, we do. Do we have an angle at the circle? Yes. Okay, so what I want you to do, and I know it's really hard when you don't have this as a hard copy in front of you. Anybody who's struggling to see this, put your finger at C and your finger at E. And you're going to come forward to M1, back to C, back to E. Now follow C and E to the circle. That gives us A1. Can you see that? Okay, so angle M1 is twice the size of angle A1. Can you see that, guys? Yes, it is, Amatle. Okay, so again, fingers at C and E, come to M1 at the center, back to C and E, go to A1 at the circle. Okay, so this is angle at center is twice angle at circumference. Okay, so first of all, before we can describe how big M1 is, we need to describe how big A1 is. You see, oh good. All right. So how are we going to describe angle A1 in terms of X? How am I going to describe A1 in terms of X? Where are we looking when we're wanting to describe A1 in terms of X? That's it, Teddy. You would just have to simplify a little bit. Perfect. Ntokozo, quite right. Okay, so Ntokozo and Teddy are looking inside the triangle. They're looking inside triangle CAF or FCA. All right, we've got that angle at F is 90. We've got angle C is X. Good. So not CAD, CAF. Amahle. Maybe it was just a little typo. The F and the D are, yeah, on very close to one another. Okay, so it's triangle CAF. I'll just highlight it quickly for you. We can always rub it off. Okay, because we've got that 90-degree corner at F. We've got that angle C is equal to X. So that's going to allow us to describe A1 in terms of X. So angles of a triangle add up to 180 degrees. So you're quite right, guys. A1 would be equal to, sorry, it's supposed to be like that, would be equal to 90 minus X. Our reason, angle sum in triangle. Okay, now M1 is going to be twice its size. Okay, so it's going to be 2 of 90 minus X, angle at center equals 2 times angle at circumference. All right, so that's going to be 180 minus 2x. 2x, Yamkela. Remember, you've got to distribute the 2 to both terms in the bracket. Okay. All right, now that was out of 3. So here it would be statement reason. They're never going to give you, so for things that are, it's stuff that you've learned in grade 8, grade 9, grade 10, grade 11. So things like angle sum and triangle, angles opposite equal sides, angles around a point, adjacent angles on a straight line, if you use that exterior angle of triangle, all of those sorts of things, you will be given 1 mark statement reason. Then when we're using stuff from grade 11. So in other words, angle at center is twice angle at circumference, or tan chord theorem, or whatever the other ones. Then they will separate it and give you or can separate it and give you a statement reason mark. Okay, so that's why. So you leave your final answer, Tuelo, as M1 equals 180 minus 2x. That would be your final answer, because they said here in terms of x. All right, so there would be a mark on the statement, and then there would be a mark on that reason, like so. Okay. Cool beans. All right. Now in 10.3. Let's go and have a look. All right. Proof, giving reasons that AD is a tangent to the circle through A, C, and F. So prove giving reasons that AD is a tangent to the circle passing through A, C, and F. Now things are getting quite a lot more difficult. Let's go and identify where A, C, and F are. Oh, we've actually done that, haven't we? I'm so silly. We were working in that triangle. And they want us to prove that AD is a tangent. So what I'm going to do here is I'm going to rub off those 90 degrees. And I'm just going to highlight this line. Okay. Teddy, you were asking in the beginning, why can't we use tan chord theorem? All right, which is a really good question, right? And I explained to you that because you had a cyclic quad on the inside and not a triangle, that tan chord theorem wouldn't apply. So if you have a triangle on the inside of a circle, like I've got over here, and if they told us, or we were able to prove that this angle over here equaled that angle over there, it means that this line here has to be a tangent to the circle. Does anybody know what I'm trying to get at with what I've drawn over here? So look at the pink triangle. and look at the line that I've highlighted. Do you see what I'm trying to get at here? Can anybody tell me the reason I'm going to use to prove this? So I've highlighted my triangle. I've highlighted the line that would be the tangent. Can anybody tell me the reason? There we go. Well done. So Yamkela, look at what Ntokozo wrote. Converse of tan chord. Good. Well done. And Nhlanhla, you're on the ball. Okay, and Nhlanhla's even identified what we need to prove. Okay, that's great. Well done. Okay, Amahle, we're not, mind you, maybe Amahle is right. Amahle is saying tangent is perpendicular to the radius. Maybe there's more than one way to do this, Amahle. Let's have a look. Okay, I think you might actually be correct, Amahle. Maybe I was wrong. Maybe we can't prove that angle A2 is equal to x and use converse tan chord theorem. All right, so yes, that's actually something to consider. When they want you to prove that a line is a tangent to a circle, there's two ways you can do it. The one way is to prove converse tan chord theorem. The other way is to prove the converse of the radius perpendicular to the tangent. And I think you're right, Amahle. I think that's what we're going to need to do. We'll explore the other option and see if it works. So I'm just going to make a note of that for you guys over here. Right. So proving a line is a tangent. Which is a question that often comes up. Number one, converse tan chord theorem. And well done to those of you that knew that. The other one, well done, Amahle, is converse radius perpendicular to tangent. Okay, so if we consider the one and it doesn't work, we can consider the other one. All right. Now, I suppose it was a bit silly of me because I went and rubbed off that right angle. But remember in the beginning, I had said to you, CMD is a diameter. It subtends a right angle at the circle. There we've actually got it. All right, because we've got this right angle over here. So yes, we can use what Amahle was suggesting. What Nhlanhla was suggesting is that we need to prove that C2 is equal to X, which is also correct, but maybe it's not possible. Maybe we don't have enough information. And Nhlanhla, I'm just having a look at angle. Hang on. Nhlanhla, we know that angle M2 is 180. We can do it your way, Nhlanhla. We can do it both ways. So we know that angle M1 was 180 minus 2x, right? So if we use adjacent angles on a straight line, we could actually describe, I know they haven't named this angle, but we could describe this angle would be equal to 2x. And then the angle at the center is twice the angle at the circumference. So A2 would be equal to X. We can do it that way. All right, so it would be possible. Or we can do it Amahle's way. We can say that angle A1 plus A2 is equal to 90, angle in a semicircle. Therefore, AD is a tangent to the circle, and then that would be converse, radius perpendicular to tangent. Hang on a second, can we? Sorry, I'm just thinking this one through. Because we don't know that CA is necessarily a radius, do we, Amahle? Let's just think about that.
No, ma'am, but
So in order to prove converse, radius, perpendicular to tangent, we're trying to prove that the line is a tangent, right? So we have to prove that the radius is perpendicular to that line. We don't actually know that CA is a radius or a diameter of that circle. So I think it's going to be better for us to go with what I originally suggested in this question. Okay. So I hope everybody can see what I have written on the screen here. We know the size of M1. Yeah, it does. It does. Let's go with that. Okay. So let's put it down on paper. Angle DME will be equal to 2x because of adjacent angles on a straight line. Therefore, and I suppose this is also mind you, I don't know if it is the quickest. Therefore, angle A2 will be equal to x because of angle at center equals 2 times angle at circumference. So now, so important, like Nhlanhla pointed out, therefore we have to state this: angle C equals angle A2 because they both equal x. Therefore, AD is a tangent and our reason is going to be converse tan chord theorem. Yes, CAF is a triangle. The circle's not drawn, but it is a triangle inside the circle. Okay, CAD is 90 angle in a semicircle. That's also true. Okay, yes, Amahle, go for it.
Ma'am, why exactly can't we use the converse of the tan is perpendicular to the diameter or radius? Because if C, F, and A are points on the circumference, then obviously the triangle would need to have a diameter or a radius.
I wonder if I'm just being silly here. You see, the thing is that when you are proving converse of tan chord theorem, just think about this. If that line is a 90-degree the line is a radius. You see, we're not allowed to do any constructions. So what you're not allowed to do in geometry is you can't, first of all, you can't do constructions. The only time that you're allowed to do constructions is when you are doing the proof of a theorem. Then you have to do a construction. But otherwise, the CAP syllabus does not actually allow for us to do constructions. My only concern with doing it the other way is that we do not know that CA, but hang on a second. We know that CA see, that doesn't necessarily, yeah, no. You see, we do not know that Oh, no, wait. You know why? You know what? I figured it out. I figured it out. I'll explain it to you. Do you know how we know? Sorry, somebody might have said it, and that's what triggered me. Do you know how we know? We can actually do it your way as well, Amatli. You know how we know? Because if we've got CAF is a circle, then if you imagine is inside a circle, so CA and F are points on the circle. We know that CA has to be the diameter of that circle because it subtends the right
Yes.
angle at the circle. That's what you were trying to say.
Yes, ma'am.
Sorry, you're
It's
quite
okay.
right.
Thank
That's
you.
absolutely perfect. Well done. So this is really nice. Okay, we get a chance to actually do this in both ways. Sometimes we don't always get an opportunity to do that. Okay, so let's put down Amahle, and I'm going to put a little heart there because you were doing some really good thinking. Okay, sorry, Amahle, it's been a bit of a long day for me. All right.
No, it's okay, ma'am.
My apologies. All right, guys. So this is what Amahle was thinking. And can you see it now, Gugu? I can see it now too. All right. If you consider triangle CAF, the fact that C and A and F are points on this invisible circle, because F is 90 degrees, CA has to be the diameter of that circle because of that 90 degree. So what we would need to establish, Amahle, is that first of all, CA is the diameter. Okay, so what we can say here is CA is actually, first of all, sorry, let's start at the beginning. Okay, angle CFA, angle CFA equals 90 given. Therefore, CA is a diameter. Now, this is another converse. This is converse angle in a semicircle. Then we're going to state that CAD equals 90. Angle in a semicircle. Therefore, AD is a tangent converse diameter perpendicular to tangent. So that's what we need to do. We first have to establish that CA is a diameter. Once we've established that CA is the diameter of circle CAF, then we can say that 90, because A1 plus A2 is 90, angle in a semicircle, AD is a tangent converse diameter perpendicular to tangent. Yeah, no, that's lovely, Amahle. Well done. That was a beautiful spot. And I'm so glad I was able to do that solution with you guys as well. Are there any questions?
I also just learned something new today.
Yeah, no, that was lovely, Amahle. Well done. You happy, Unati? Cool. All right, so that was out of 4. So it would be statement, reason, statement, probably statement, reason here again, or maybe statement, reason, and then here statement and there reason. Okay. Sure, no problem. So that's the cool thing about geometry, is that there's often more than one way to do something. And it's lovely when we can do something in more than one way, because that really helps to deepen and strengthen our understanding of something. Okay, so we have to prove that this is a diameter, statement and reason. And then here, that would be statement, reason, and then our reason, like so. Okay, cool beans. Awesome stuff. All right, let's do question 10.4. So now we have been given that CF is 6 units long. Okay, so we'll put the 6 in there. And AB is 24 units. Calculate, now here we've got a little bit of a, oh, I hope we're going to get to the end of this. Calculate, giving reasons, the length of AE. What do you guys think we're going to use here? Indeed, because we've got these two right-angled triangles. Remember, that's also a right-angled triangle. Okay, so any ideas where we should start with this? I just want to give you guys an opportunity to think it through as well. They've given us CF as 6. They've given us AB is 24. We've actually got 3 right-angled triangles. They want us to calculate the length of AE. So Nkandla is saying AE squared equals BE squared. AE squared equals BE squared minus BA squared. All right, fine. That's a fair statement. So with that one, what Nkandla's doing, we don't have BE quite right. And we know that BM equals ME, and we know that CM equals MD. They're all radii. See, I don't know if we could do that, Leanne, because first of all, we're not going to do the sine rule in a triangle that's not right angled. But that being said, that doesn't mean, yeah, you see, we don't have the size of any angles, because what we can always do is if we've got a right angle triangle, we can always use our basic trig ratios. But in this case, we don't know the size of X. What I do think they will probably want us to do with this question is that in order to calculate the length of AE is made up of AF and FE, which are equal to each other. So I'm thinking they probably want us to calculate the length of AF and then double it. So is there a way from the information that we've been given that we can work out what AF is? Yamkela. So we're thinking about midpoint theorem. Okay, but in order to use midpoint theorem, we have to have parallel lines. We don't have any parallel lines. We can also use line through midpoint parallel to second side, but we don't have any parallel lines in this case? Has it given us any other information that we have missed here? Why are you confused, Gugu? So what you need to do, Gugu, all right, first of all, is don't be overwhelmed by the question, all right? What we've got to try and do is break it down and figure out what things we know that can help us to answer this particular question. And we've got some really good things here, all right? So we've got Pythagoras, for example. We just haven't figured out how we're going to put it all together just yet. It has to be the theorem of Pythagoras because we've got right-angled triangles. And the minute they start giving us the lengths of sides, then it's more than likely going to be the theorem of the theorem of Pythagoras. They're not going to expect us to work outside of our curriculum. So they don't expect us to work with anything that we don't know. There's got to be an answer to this based on what we already know. I think what I'm going to do with this particular question is, have you guys taken screenshots? Yes. Okay. All right. If we run out of time, we will come back to this. Now, Yamkele, you're saying that EM equals MB. Where do you get 18 from? Okay, but where do you get 18 from? I just don't understand. I agree. CM equals MD and BM equals ME. They're all radii. But why on the 6 units? 1%. I don't understand why you guys are saying 6 times 3. Hang on a second. Do you know what I think we're going to have to do here? I said we don't have parallel lines, but maybe that's not true. We know that we've got this right angle over here. And can you see? So in other words, what I'm looking at, guys, is this. Let's just get rid of all of the pink because it makes it a little bit confusing, right? This is a bit hard for us to see initially. Remember, we also agreed in the beginning that A2 plus A3 was equal to 90. Do you remember that? Okay. So if you consider you've got a 90-degree angle there, now you've got a 90-degree angle over there. So these two lines are going to be parallel to one another. In other words, this line here and that line there will be parallel because alternate angles are equal. Can you see that? Yes.
Please don't mind me running the
No,
phone
that's
in the
fine. Okay,
background.
so what I'll do is I'll come back to this question and I'll do it with you guys because this is what it is. It's we first have to prove that those lines were parallel, and then we're going to use I don't think it's midpoint theorem. I think it's line through midpoint parallel to second side, and then we're going to do the theorem of Pythagoras. But I'll do the solution with you next time. Sorry.